Hej, jag är Valentin, jag är forskare vid Linköpings universitet och jag ska berätta om arbetet vi gjorde med en fransk student, stödd av Frankrikes regering, som besökte oss en sommar för ett par år sedan. Vi tackar Vetenskapsrådet och Trafikverket för stöd till projektet PBN för UTM, som vi driver tillsammans med LFV. Nu kommer jag byta till engelska för bland annat för att förklara förkortningar och faktiskt för resten av presentationen. UTM stands for Unmanned Traffic Management, the system under development to manage drone traffic which will soon hopefully take off into the skies of our cities. PBN stands for Performance-Based Navigation, which is one of the pillars of modernization of the current air traffic management. The current ATM was created under the paradigm of one size fits all. For instance, if you look at these charts, you may sometimes see indications like what I saw in a Bromma chart, a little arrow saying slower traffic, keep right to get out of the faster guy's way. But in general, all aircraft are assumed to use the same route network. PBN recognizes the diversity of airspace users. If someone invested in precision navigation equipment, why not give the user a preferred route? This is called performance-based service. In the conventional ATM, the user's diversity has been recognized quite recently, and PBN has to be retrofitted into the system. The diversity of the drones is apparent, and it would be nice to have PBN in UTM already from day one. In ATM, the issue of limited airspace capacity has been acknowledged both by aviation professionals and even by the general public. The fact that the traffic is three-dimensional makes its management, on the one hand, only harder. On the other hand, the third dimension may be used to deconflict the traffic by distributing the vehicles among layers of the airspace. Such distribution, for instance the alternating altitude rule, is widely in use and has been well researched in ATM. In particular, Cesar's Metropolis project, which now should perhaps be called Metropolis 1, since we are currently working on Metropolis 2, considered several ATM concepts, from more or less free flight to highly structured traffic along highways in the sky, and determined that the layers concept is actually the winning one. Metropolis assumed that the aircraft are uniformly distributed over the region of interest, and hence the same number of layers will be used everywhere. However, most likely, drones will be distributed highly non-uniformly over a city. Here on the left is the map of Norrköping, the heat map is the population density, and on the right is the likelihood of seeing a drone in different parts of the city, which we computed using drone traffic simulation. It can be seen that there will be many more drones in the city center than in the outskirts. So in this work, we propose to take the traffic distribution into account and establish different number of layers over different areas. We do it fully automatically, so the layer structure can be recomputed as often as needed, adapting to the traffic density and leading to something that may be called software-defined airspace. In fact, determining drones' performance requirements is one of the main stumbling blocks to unleashing the societal potential of the drones industry. Without the requirements, the regulators don't know how good the drones must be in order to be allowed over a city, and the manufacturers don't know how to produce the good enough drones. Our work both suggests performance needs and relies on PBN in UTM. Indeed, only a thin band of airspace will be available for metropolitan drone operations. The very low-level uncontrolled urban airspace extends up only to 150 meters. And in addition, the drones should not be allowed to fly too low due to privacy and other public concerns. Thus, to fly in areas with larger number of layers, the drones may be required to have better vertical precision, and also the drones on lower, potentially more preferred layers may need to be quieter. Several features of PBN for UTM explored by us are often mentioned by Dr. Parimal Kopardarkar, the PI of NASA's UTM project, with whom we keep close connection. PK's thoughts have been echoed many times, in particular in various canopses. Canopses are mostly visionary documents, and we are trying to show how the features of envisioned UTM system may actually be potentially implemented. So now I turn to the technical part of the talk, explaining what exactly we did to come up with the layered airspace structure. We modeled the drones by disks of certain radius, representing the safety zones around the drones. Overlapping disks means loss of separation. The drones must be put into different layers to avoid potential collision. We say that a set of drones forms a clique if the disks intersect pairwise. That is, any two drones in a clique are in conflict with each other, and hence, to resolve the conflicts in the clique, each drone must occupy its own separate layer. The number of layers is equal to the size of the clique, that is the number of drones in the clique. One question of interest is what's the largest number of layers that we will need? Or what's the largest clique size? Or more broadly, why is this number small? Maybe all drones at some moment will meet in a single point. The answer is given by a probabilistic traffic analysis. In aviation, uncertainty is treated as a nuisance and a lot of research is devoted to coping with it. But for us, non-determinism is a friend. We can't prevent someone buying 10 drones and throwing them on top of each other, creating a large conflict clique. But under nominal operations of non-malicious users, we shouldn't be afraid of probabilities. We can estimate them and handle the conflicts effectively. Come to think of it, the number of conflicts increases with the increase of the conflict radius. If the drones have better navigation performance, they conflict more rarely. The conflict severity, which we measure by the size of the clique, increases also with the traffic intensity, which we measure by the expected number of flights. In our previous project, UTM-OK, also financed by Trafikverket and run with LFV, we determined that the probability of having a large-scale conflict has the threshold dependence on traffic intensity. When the number of flights is small, the probability is essentially zero, and as the intensity increases, the probability jumps to 1 quite sharply. This is true for any conflict radius. And the final output from UTM-OK project, UTM-OK stands for UTM Optimierung och Kapazitet, were graphs like here on the left, showing how probability of large-scale conflict depends on the radius and traffic intensity. On the right is the same graph, but viewed from the top. It can be seen that the boundary between having the conflict with probability 1 and having conflicts with probability essentially 0 is quite sharp. The boundary is the airspace capacity threshold. When putting in more traffic will definitely lead to larger conflicts, larger cliques. Let us now look how this capacity threshold depends on the size of the conflict, that is the number of drones in the clique. Cliques of size 2 will appear very soon for low traffic and radius. For cliques of size 3, the capacity is a bit larger. Size 3 cliques appear for larger N and larger R. Cliques of size 4 appear even later, and so are cliques of size 5, 6, 7, 8, and so on. Cliques of size 11 will not appear or appear with probability close to 0, even for high traffic intensity and conflict radius. The capacity thresholds are all we need to know. Indeed, given a particular day of operations, say this many drones with such radius, we are sure that we will not see cliques of size 11. Cliques of size 10 also have 0 probability, and so are cliques of size 9, 8, 7, 6, and even 5. But cliques of size 4 may indeed appear, and cliques of size 3. And cliques of size 2 will appear with probability 1. So we know the largest clique has size 4, but we don't want to have 4 layers everywhere in the city. Instead, we look at where size 4 clicks happen and establish 4 layers only there by taking the convex hull of all such conflicts. Recursively, we geofence the size 3 clicks into their convex hull and size 2 clicks into their convex hull. And here's how our layered airspace will look like over Norrköping. Here is for another intensity and conflict radius. And here are just some more results. All in all, we suggested a way to define layered airspace over a metropolitan area. Our algorithms are simple, but their justification is deeply rooted in prior results on safety thresholds for drone traffic. One delimitation of our solution is the assumption that the ground level is constant over the city. Currently, we are taking into account the terrain or city height profiles to establish different flight levels in different parts of the region of interest. But that's hopefully is a story for next time, and today I just want to thank you for your attention.